section 8.2, we're going to begin predicting the products from a given chemical reaction. What we will have here is we're going to break this down into 5 different main categories of reactions in which there are some subgroups. And from this, we'll do the predicting of products in a chemical reaction. They're not all this simple, and this is only covering part of them, but A plus B, what does it make? Or in the case of some other examples, it's not quite A plus B, but that's what it is. We're trying to figure out what the heck's going to happen on the right-hand side. Now, if we look at our examples here, a couple things that we're going to do is these equations. We're going to talk about what's called synthesis, decomposition, replacement, in which are single and double, and then combustion reactions. This is only a sliver of chemical reactions, but these are the 5 most common that you always begin with. So after we've identified the type of equation, then we're going to predict the products given a set of reactants. So we have these 5 groups: synthesis, decomposition, single replacement or displacement, double, and then combustion. We've got a 1 or 2 letter abbreviation just so you don't have to write it all the way out. And then the numbers off to the side talk about the number of subgroups. There's actually 2 synthesis reactions we'll look at. There's actually 4 decomposition reactions we're going to look at, and so on. Now, 2 things to think about as we do these. Number 1, we're always going to assume the reaction's spontaneous. We're always going to assume it's going to happen no matter what. In reality, there are some reactions that don't occur. So we're, might be saying, well, hypothetically. But for our purpose, everything we assume occurs. And number 2, unless we're told otherwise, we don't expect there to be any special conditions. If there are special conditions, then we've got to be given those. We're not going to be able to make any assumptions on what the special conditions are, if it'll happen or if it will not happen. And everything's got to be pretty much laid out for us. So we go through these. The first one we're going to look at, synthesis reactions. What I'm going to start out with each one of these groups or these 5 categories is sort of a generic equation. So in the terms of synthesis, what we basically have is we're just going to start out with 2 things, and somehow they join together to make one thing. So 2 chemicals make 1 chemical. Whenever you see an equation that has that structure, 2 reactants making 1 product, that's what we call a synthesis reaction. And again, we're assuming they're spontaneous. There are 2 subgroups of reactions. The first subgroup is where we have a metal by itself, and it reacts with a nonmetal that's by itself. This basically goes back to just the simple naming examples that we did back in chapter 7. And if they react, they're going to go together. So let's start off simple. If I take sodium, which is a metal, and I react it with chlorine, which is a nonmetal. Now, remember, chlorine is one of those diatomic elements. If Na and Cl were to bond together, they would form in the 1-to-1 ratio, right? Sodium's a +1, chlorine's a -1, NaCl. So there's our skeleton equation. 2 reactants join together to make 1 product. Now, we still need to go through and do the balancing we did back in section 1. So if I have a diatomic chlorine, I got 2 chlorines on the left, I need 2 on the right. If I got 2 sodiums on the right, I need 2 on the left. Give you one more example. Let's say we take magnesium and we react it with sulfur. Sulfur is not one of the diatomics. So magnesium's a +2, sulfur's a -2. They're just going to form MgS. Now, what I would suggest here is that you do 2 more examples that fit this pattern, and at some point in class, show me to make sure that you understand what you're doing here on this. But it's that simple. Now, what you've got to be able to do is you've got to be able to recognize this original setup, this generic setup. And if you recognize that, then you know what to do. The second subgroup is where we take a metal oxide and it bonds or reacts with water to form a metal hydroxide. Now, I got all these X's and Y's here, but what you need to recognize is these subscripts can change. But basically, we have a metal bonded to oxygen that reacts with water, and then the metal becomes bonded with hydroxide ions. Now, X's and Y's, we don't know what these subscripts are until we know what the metal is. But again, we see a reaction on the left-hand side, and it says a metal oxide plus water. We know, oh, it's got to make the metal OH. So let's say we start off with calcium oxide, and it reacts with water. What we've got to recognize is that metal oxide and water, they join together to make one chemical, and that chemical is a calcium hydroxide. Now, we formed a hydroxide. Hydroxides are OHs are -1 charge. Calcium's a 2 plus. When calcium bonds to hydroxide, we get CaOH2. Always after we write the formula, we always have to balance. We double check everything is balanced. Let's say we take sodium, or where did sodium? Let's say lithium hydroxide. Lithium is a +1, oxygen's -2. We bond it with water, or react it with water. That lithium is going to bond with hydroxide ions. So what's going to happen is all those H's and OH's rearrange. So we're going to get lithiums now bonded to hydroxides. Now, we don't have to put the parentheses because they're +1, -1. So you can do either LiOH with parentheses or LiOH without parentheses. Now from here, we still need to balance. I got 2 lithiums on the left, need 2 on the right. Got 2 H's on the left, 2 H's on the right. I got 2 O's on the left, 2 O's on the right. Remember, these coefficients out in front, it's kind of like in a math equation, they distribute everything that comes after it. A subscript within the equation distributes only what's right before it in the parentheses. So, again, get the pattern here. Pick 2 other metals, bond them to oxygen, react them with water, figure out what the products would be, and show them to me at some point in class. All right, moving along here. Decomposition. Now, decomposition is the exact opposite of synthesis. Now, these are not traditionally spontaneous. Usually they're going to have to be somehow forced to. And the most common way that they are forced is heat or even electricity. So, there are 4 subgroups that we're going to look at. The first subgroup is the decomposition of a binary compound. So we're talking about a chemical that has just 2 elements in it. So again, if you recognize here, if you have one chemical on the left-hand side, the only thing that it can do is break apart. Now, they're probably going to tell you something here about the conditions. What did they do to make it happen? We do a simple one here. NaCl. If we heat it, then we can break the sodium atoms away from the chlorine atoms. Now, when chlorine atoms are by themselves, they're not individual. They're not one atoms, by themselves. They're always in pairs. So, if I have a salt, a salt structure breaks apart, it's going to make a sodium and it's going to make a chlorine pair, a diatomic molecule. Again, it's not balanced, so really what we have to have happen is 2 salts decompose into 2 sodium atoms and a chlorine pair. So again, what it is, 2 NaCl's break apart, and we get 2 sodium atoms and a chlorine pair. Another simple example is just plain old water. Water can decompose into hydrogen gas and oxygen gas, the 2 elements. Again, we have to balance here. 2 water molecules will break apart into 2 hydrogen pairs and 1 oxygen pair. Again, if we can imagine here, let me write this. Two hydrogen pairs and an oxygen pair. Okay, make up 2 more examples. Show them to me in class. Next one, decomposition of a metal hydroxide. So again, this is the reverse of synthesis number 2. If we go back to synthesis number 2, metal oxide plus water makes the metal hydroxide. Now we've got the decomposition of a metal hydroxide. A metal hydroxide breaks apart into a metal oxide and water. So here, metal hydroxide, a metal OH, a metal bonded hydroxide, when heated, okay, again, this is not spontaneous, it's got to be heated, will then separate back apart into the metal and oxygen and water. So we could have something like, let's say, calcium hydroxide. Okay? Calcium bonded to hydroxide plus 2 minus 1. When heated, the calcium will stay bonded to the oxygens, okay, plus 2 minus 2. And then some of the oxygens and the hydrogens will break off to form waters. And if we notice here, the equation is balanced. We could have something else, let's say potassium hydroxide, KOH. Okay. Potassium plus 1, hydroxide minus 1. Potassium breaks apart and is left with just oxygens. It's K2O. Again, potassium plus 1, oxygen minus 2. And then water molecules. Now, in this example, it's not balanced. So the only way this is going to work is if 2 KOHs break apart. Then we'll get a K2O and a water molecule. As in the past, examples. Do 2 more. Randomly pick a different element. Also, don't stay with the same charge. Just because I did potassium here, don't do a sodium and lithium because they're also plus 1. Change up the charges. Third one, decomposition of a metal carbonate. So here we have a metal bonded to CO3s that then form metal oxide and carbon dioxide. So we have a metal bonded to the carbonate ion. Again, all the X's and Y's, I just put those up there because, again, depending upon the element, we're going to have different charges. If we have different charges, then that changes all the subscripts. Let's pick one here. Say sodium carbonate. Sodium's a plus 1, carbonate's a minus 2. If this is heated, and again, most decomposition are not spontaneous, so if we heat it, the sodium will decompose and bond with just the oxygens, and then the carbons will bond with any remaining oxygens to make carbon dioxide. If we look here, sodiums are balanced. Everything's balanced the way it is. Let's look at another one here, strontium carbonate. Strontium plus 2, carbonate minus 2. If that decomposes, we get strontium bonding with oxygens, and then we get carbon dioxide. So what we're going to see here is it doesn't matter what the metal is. Everything does exactly the same thing. The only thing that changes is subscripts, and that's only if charges change. All right, so 2 here. Figure out 2 other ones. Again, pick some D metals, change it up. Don't always pick the same ones. Last one, decomposition of a metal chlorate. So chlorate, ClO3, it has a 1 minus charge. So let's say I pick copper chlorate. I'll say copper 2 chlorate. Copper is a 2 plus charge. Copper 2 chlorate. If this is heated and decomposed, we're going to get copper 2 with chlorine. Okay. Copper 2 is a 2 plus. Again, I'm putting the Roman numeral 2 up here just for a reminder. The question would tell you which copper. Otherwise, you can pick one if you're just doing it for an example. So what's going to happen here is when we heat it, all the oxygens break off by themselves in pairs, and the copper stays with the chlorine. If we look here, we have 2 chlorines, and we have 6 oxygens. Again, 2 chlorines, 6 oxygens. we put a 3 out in front. Let's say we pick iron 3 chlorate. So iron's a 3 plus, chlorate's a minus 1. Decomposes, iron bonds with chlorine, plus 3 minus 1. And we get oxygens. The only difference here is we got to kind of balance. Got 3 chlorines there. I've got 3 chlorines here. I got 9 oxygens there. I can't. I put a 4 out in front. I get 8. I put a 4 back behind, or a 5 out in front. I get 10. I really need 9. So really, what I got to do is, if I double this, that gives me 2 irons and 6 chlorines. If I do that, that gives me 2 irons and 6 chlorines. Now I have 9 oxygens times 2, which is 18. Now I have 9 O2s, which are 18 oxygen atoms. Now, I kind of went through those quick. First of all here, 2 examples. Okay? So, as you go through these, change the metals. Don't always pick the same charges. And I want you to get just comfortable with using different examples, different combinations to get different charges, different subscripts, so that you feel comfortable doing these. We're halfway there through all these different types, and we've just done the hardest ones. These decomposition ones are the ones that are the most difficult to do, especially these last 3, the decomposition of the metal chlorate, metal carbonate, and metal hydroxide. So spend some time, make sure that you're working on these, and then the second video will look at the replacement or displacement reactions, and then finally the combustion reaction.